Hey there, welcome back to our channel. If you've been following along, you'll remember that in our previous video, we showed you how to create a blend font light model in WebGPU. The blend font model produces great results, but in the real world, we encounter various types of lights, each with its own unique behavior. In today's video, we'll be discussing the point light model. A point light is a light source positioned somewhere in a scene that illuminates in all directions. It's similar to a light bulb, radiating light that fades out as it travels further away. Take a look at this illustration to get a better idea. Now, the blend font model we discussed in the last video can be thought of as an idealized point light. It scatters light in all directions, but the light rays from the source never diminish, creating an effect of an extremely strong light. However, in most 3D applications, we want to simulate a point light that illuminates only a specific area near the light source, rather than the entire scene. To achieve this, we introduce the concept of attenuation, which reduces the intensity of a point light over distance. We can use the following formula to calculate attenuation based on the distance between the object and the light source. In this formula, d represents the distance, and we have three constants: the constant term kc, the linear term kl, and the quadratic term kq. The constant term is usually set to 1, the linear term reduces light intensity linearly, and the quadratic term provides a quadratic decrease in intensity for the light source. Alright, let's dive into the programming aspect now. We will start with the project we worked on in our last video. If you already have the project on your local machine, simply open it using Visual Studio Code. If not, don't worry, you can easily download the project from our GitHub repository using the command git clone followed by the branch name and the repository URL link. This will download the project onto your local machine. Simply open this project using Visual Studio Code, and then use the command npm install to install all npm packages required by this example. At this point, we will update WebGPU package to the latest version. From the package.sin file, you can see that the version of WebGPU is 0.1.31, while the latest version is 0.1.34. We also need to update the type of script from 4.6.3 to latest 5.1.3. And update the WebGPU simplified package from 0.1.33 to 0.1.34. Now, let's implement the point light model in the shader code. Open the package.sin file. You can double check that we already update WebGPU types. WebGPU simplified package, and type a script to the latest version. Create a new fragment shader file called pointfrag.wdsl in the section 02 folder, and insert the following code into it. This fragment shader is similar to the blend font light model we used in our previous video. The key difference is that we now incorporate the attenuation into the light model and include in the lighting calculations. To achieve this, we simply multiply the attenuation value with the final color. In this example, we'll explore how to effectively add point lighting to multiply 3D objects using WebGPU's instance drawing feature. Instance drawing allows us to draw multiple instances of the same object with a single call to the drawIndexed function, resulting in faster rendering time. For this demonstration, we will create multiple instances of two types of shapes, cubes and spheres. To begin, we need to implement the vertex shader for our instance drawing. Create a new vertex shader file called shaderinstancevert.wdsl in the section 02 folder, and insert the following code into it. The reason for using arrays of mat 4x4 matrices for model matrix and normal matrix and an array of vec4 vectors for color vector is to enable the creation of multiple instances for each shape, each with different locations and colors. To pass these arrays, we use storage buffers since their sizes are unspecified. Runtime-sized arrays in WebGPU can only be used in the storage address space. However, the view projection metric remains in the uniform buffer because all instances will have the same view projection metrics. Within the VS main function, the built-in instance index parameter is used to represent the transformation and color for each instance, and the position, normal, and color for each instance are processed as output. The fragment shader then uses this output to calculate the lighting effect and color. Now add a new type of script file named pointlight.ts and paste the code to the file. This example follows the similar structure to the one used in the previous video. The create pipeline function has been updated to accept an additional input parameter, the number of objects parameter, which represents the total number of instances for all types of shapes in this demonstration. Inside the create pipeline function, we generate vertex, normal, and index buffers for the cube and sphere shapes. We then define the uniform and storage buffers for the transformations and colors. Here, we utilize the create buffer function from the WebGPU simplified package to create storage buffers by specifying the buffer type and noun as storage. Within the draw function, we begin by rendering the cube instances, followed by the sphere instances. Using this code snippet, it is important to set the first instance parameter accurately to avoid instances overlapping each other. In the run function, we create total of 200 instances, including 100 cube instances and 100 sphere instances. This code block allows us to define the model and normal matrices, along with color for each instance using the random math function. This will create a distinct location, orientation, and color for each instance. Here, we have added the linear and quadratic attenuation parameters for the point light to the data gate control, which allows us to examine their effect on the light by changing the parameters with the mouse. We have also animated the position of the point light source within the frame function, so you can see real-time changes in the lighting effect in the scene. Now, let's proceed to add this example to the navigation menu. Open the site nav.html file from the src.html folder, and add the following link point light. Once we have done, we can proceed to build and compile the code by executing the command npm run prot in the terminal window. Then, clicking on the Go Live to open the default web browser and view the 3D objects with point lighting in action. You can see that only the objects in the front are lit, with the closest objects being the brightest. The objects in the back are not lit since they are too far away from the light source. You can change the linear or quadratic terms to examine the attenuation effect on the light brightness. Now let's conclude today's video. In the next installment, we will discuss the Spotlight model in WebGPU. Make sure to stay tuned for that upcoming video. Thank you so much for watching today's video. I hope you found it informative and helpful for your WebGPU development journey. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more exciting content. If you have any questions or comments, feel free to leave them down below. Until next time, happy coding.